Oh, may I start?
No, just a moment.
Okay. Well, yes, we have 1 minute, 2 minutes.
2 minutes, yeah.
Yeah.
Юрій Анатольович, це нагадування про минулі конференції.
Я бачу.
Okay. So with a great pleasure, let me introduce our next speaker, Professor Yuriy Drozd from Institute of Mathematics of National Academy of Sciences of Ukraine. And the title of his talk is on Backström rings and group action.
Thank you.
Yes, please, you may share your presentation.
Okay.
Yes, you can start.
So thank you for this opportunity to present this talk on so serious and so representative. I have to present it. Yeah. Well, this investigation arose as a part of our common projects with Igor Burban and Andriana Plakash for 2 different projects, but they have some intersection. Yeah. And so I will not start with examples and history. I will do it in a couple of minutes. And now I want So I will start with definitions and examples and maybe some history. And then I consider technical tools which I use. So often the envelope introduced by Igor Burban and me, categorical resolution related to this standard envelope and semi-orthogonal decomposition. Then, after again some examples, I should consider group action and a new class of orders, so-called almost Backström orders. So I will start with definition. Let A and H be a pair of semi-perfect rings. This pair is called Backström if these rings have common radicals. I recall that semi-perfect means that the quotient by radical is semi-simple and the idempotence can be lifted modular radical. It was introduced by Bass. Moreover, this pair is called hereditary if the ring H is hereditary, and piecewise hereditary if H is piecewise hereditary. I recall that means that it is derived equivalent to a hereditary ring. It has a derived category equivalent to derived category of a hereditary. If there is a hereditary pair H, then the ring A is called Backström ring. Correspondingly, if this pair is piecewise hereditary, piecewise Backström ring. By C or CFAH, I denote the conductor of H and A, the annihilator of the quotient. One can easily check that this definition is left-right symmetric, so it doesn't matter when we consider this quotient as right module on the left module. And C actually C is the biggest H ideal contained in A. Now about a bit history. First, the Backström rings appeared in PhD thesis of Backström in 1972, where he considered the orders such that the endomorphism ring is hereditary. Ring in some years, Ringel and Ogenkam showed that torsion-free models of a Backström hurdle correspond to representation of a quiver naturally related to it. And a bit later, Ogenkam described the Auslander-Reiter quiver of such order. It is very much like the Auslander-Reiter quiver of the quiver, and with some gluing. Pair is called nodal if, moreover, the length of tensor product of any simple A model with H is at most 2, length of A. And if there is a hereditary nodal pair, AH, then the ring A is called nodal. Nodal orders appears in my work when I considered the rings such that the classification problem for all finite models is tame. The derived categories of nodal rings were described by Igor Burman and me. They are also tame, so there is a complete description of these categories. And then Zembe considered finite dimensional nodal algebra and proved that gentle and skewed gentle algebras are Backström. Now I recall that a gentle algebra is a basic algebra if it is a quotient of an algebra of a path of in a quiver by an ideal generated by some products of two errors, and such that each vertex has at most incoming and most two outcoming arrows. And if it is a target of some arrow B and the source of two arrows, then either one of these two products, exactly one, is 0. And the same if it is the source of B and the target of A. So this picture, we have either two blue arrows, or we have blue and some red, and product, say, of blue and red is 0, but not the product of two blue or two red. Okay, skewed gentle algebras are obtained from gentle algebras by gluing and blowing up vertices. One more example, consider the ring of upper triangular matrices of a skewed field and its subring of unitriangular matrices, the matrices that all diagonal elements are. Then H is hereditary, it's well known, and the radicals of A and H coincide. So the ring of unitriangular matrices is the Backström algebra. In this case, one can easily see that this conductor coincides with radical. One more interesting example, let's consider this quotient of polynomial ring by the square of maximal ideal. It embeds into the product of simplest quivers with one arrow. Yeah, just map X A to A. And obviously under this embedding, the radicals coincide. So this algebra is also a Backström algebra. Even very good, the corresponding hereditary algebra is one of the simplest, and maybe the simplest, non-semi-simple. One more example, consider the local ring of a singular point of an algebraic curve of an algebraically closed field. One can prove that it is Backström if and only if it is formally equivalent to the intersection point of coordinate lines in an affine space. Like this, so this three-dimensional space with your three coordinate lines and their intersection point. I recall that formally equivalent means that their completions are isomorphic. In particular, it is nodal if and only if it is formally equivalent to the singular point of a nodal cubic like this. Yeah, intersection of two branches, transversal intersection of two branches. Now I consider an important tool, maybe the most important tool in the consideration Backström algebras. This is their Auslander envelope introduced by Igor Burman and me. Namely, the Auslander envelope of a Backström pair is the endomorphic ring of this direct sum of A and H over A. And for technical reason, it is more convenient to consider the opposite ring. Namely, this ring can be identified with the ring of matrices of this form, 2 by 2 matrices with coordinates in A, H, and so on. And I also consider the following ring, just replace A here by H. One will easily see that their radicals coincide. So this is also a Backström pair. In particular, if H is hereditary, then H tilde is also hereditary. And so the A tilde is Backström ring. And one can calculate the global dimension of this ring. It is okay. It so happens that it mainly depends on the ring H. So first decompose A into direct sum of modules A0 and A1 such that A1 be the maximal direct sum and such that HA1 equals A1. It can be empty, of course, no zero. And let Ri be the radical of A. Then suppose that either A is left perfect or A is left Noetherian and H is finitely generated as left A model, so also left Noetherian. Then we can calculate the global dimension of A tilde. It is 1 plus global dimension X H if the projective dimension of the first part of radical is bigger, and equal global dimension if it is smaller than the projective dimensions. And the global dimension of H tilde equals the global dimension of H. In particular, if A is a Backström ring, so it's A tilde, and then global dimension of A tilde is more 2. And it is equal to if A is not hereditary. The most important thing about the Auslander envelope is that it produces a categorical resolution of A. Namely, there is a recurrent diagram between their categories of modules. This is a diagram of this sort with the following properties. The functors f and I are exact. F star and F are correspondingly right and left and right adjoints of F, and the same for I. Okay, so in particular, F star and I star are right exact, and F clink is left exact, and it's both injunctions morphism from identity functor of A modules. And back are isomorphism. Namely, in this diagram, this functor F tilde, and so on, F is just the home from P, or where P is the first column of this projective model, the first column. P check is its dual right projective model. That's the first row. H. F star is the left adjoint to whom with this tensor product. And this one is right adjoint to tensor product is home. Taking the right factor will obtain analogous requirements for derived categories. And note that the functor df, this functor, that df, why I write df? Because f is exact, so we can calculate it. It has both left and right adjoint, which are coincident, just we apply f component-wise complexes. Yeah. Df maps bounded complexes to bounded and its left adjoint map perfect complexes to perfect complexes. I recall perfect complexes are compact objects of the right category, or just complexes, finite complexes of finitely generated projective models. So we have the following diagram. This is bounded derived categories, perfect derived categories. And if we take the product, and then it is identity of the product. If A tilde is appearance and its global dimension is finite, then this perfect category of A tilde is just the bounded derived category at finitely generated. Now this category, the category, this kernel category, if we take kernel F, it is identified with quotient, with models of the quotient of A over C, over a semi-simple ring, so it is very simple. So categories of A tilde models and A models are very close to each other. They differ by models of a semi-simple ring. On the contrary, if we consider derived categories, it is not the same. The kernel of the F is not usually equivalent to the kernel, the derived category of Q. So it consists of complexes such that all cohomologies are Q models, but not, it is not the same. It is very interesting. There is another recallment diagram arising from another functor, from functor G, which is constructed just like F, but we consider the second column, this one. And respectively, okay. And this time, if the things are better, this kernel is equivalent to the derived category of the quotient, H modulo C, and this is again a semi-simple ring. So the composable object of this kernel are identified with shifted simple models over this quotient. There are finitely many of them, that's very easy. Moreover, there are semi-orthogonal decompositions of D, even two of them as kernel DG, both have kernel DG, but here we have the image of LG star, and here we have the image of RG. Yeah. These things, these components are equivalent, but do not coincide. Recall that semi-orthogonal means that there are no homomorphisms from right to the left, from the second part to the first part, and moreover, for every object of this derived category, there is exact triangle starting from in the first part and then following by the second part. It implies corollaries for the derived dimension. The derived dimension is just Rouquier dimension of the perfect derived category. Recall that the Rouquier dimension of a triangulated category is defined as follows. First, we consider for each subset of objects, we could consider the smallest subcategory containing M and closed on the direct sums and shifts. Then for two triangulated subcategory, we denote by this thing, the smallest subcategory containing all objects such that there is an exact triangle of this sort. And then we just start with M0, which is just M, this smallest subcategory containing and so on. And then define the next step as this dagger of M and M preceding step. And the Rouquier dimension is the smallest n such that on the n plus first step, we obtain the whole category P. The semi-orthogonal decomposition, yeah, we have this one. The first one is the derived category of semi-simple rings, so its derived dimension is 0. The second part is equivalent to the derived category of H. Yeah, and then we have this diagram. We have this DG, a very good function. So, and I recall also that if H is hereditary, so this derived dimension is at most 1. That was proved by also by Rokia. Yeah. Then, so we have the following theorem that derived dimension of A is a derived dimension, at most derived dimension of H plus 1. In particular, if H is an almost Backström ring, and the derived dimension of H is 1. So we have derived dimension of A is at most 2. Moreover, there is a wonderful case when this is an almost Backström algebra of Dynkin type, which means that H is derived equivalent to a hereditary algebra of finite representation type, which corresponds to Dynkin diagram. Then the derived dimension of A is 1, because also the derived dimension of almost Backström algebra of Dynkin type is also 0. For instance, let's consider this algebra of unitary angular matrices. The corresponding hereditary algebra is of finite representation type. That is Dynkin algebra. It's of type AN. Yeah, so H is Backström algebra, and the same is for this quotient. So both of them are of derived dimension 1, not 0. Now consider group action on Backström pairs. Let we have a Backström pair and a group. Then what is an action? An action is a homomorphism from G to the automorphism group of H, and as factor set lambda, which is a function of 2 variables in multiplicative group of A, the group of invertible elements of A, such that I denote by A sigma the phi sigma of A and lambda sigma tau, the usual notations. Yeah. And then I suppose that sigma maps A to A, the subring of A maps to subring A. Then if we apply tau and then sigma, it is almost the same as apply the product. Almost the same means that they differ by this inner automorphism corresponding to this factor set lambda sigma tau. And factor set must satisfy this condition. Yeah. The cohomology condition. If we take some Backström pair, we can consider the cross products. Yeah. It is a very old thing. It is defined in the theory of rings of Jacobson. Yeah. It is almost the same as group ring, but the only thing is that we apply sigma when we twist it by sigma and lambda. I will not precise it right now. And we have the following theorem. Suppose that the finite group G of order n acts on a Backström pair, and n is invertible in A. Then the pair of cross products is also a Backström pair, and its Auslander envelope is the cross product Auslander envelope by G. Yeah. One is easily see that G acts also on Auslander envelope. And if H is hereditary, hence A is Backström, so is H the cross product of H and G. So A cross product A and G is also Backström. And moreover, if A is nodal, so is their cross product. I think these are something new. Now, I pass to the case of orders of a discrete valuation ring. I recall that an order is an R algebra, which is finitely generated and free as R model. R is a discrete valuation ring. We always suppose that this order is semi-prime, so without nilpotent ideals. Then its tensor product with the field of fractions is a semi-simple Q algebra. We always consider A as its subring. Let's consider the endomorphism ring of the radical, say as of A right module. Obviously, A embeds into A prime, and it is known, it was proved by Yakobinsky and Kirichenko and me, that A coincides with A dash if and only if A is hereditary. So this pair and A dash is a Backström pair, always a Backström pair. And it is a Backström pair if and only if A dash is hereditary. It is also a hereditary Backström pair. Then A is called a Backström order. That was the original of this term Backström. Note that if group G acts on A, then it's X on the radical and X on A dash. Yeah, so the section can be naturally extended to the action on this Backström pair. So we have the following corollary. Suppose that the finite group of order n acts on an order A and n is divisible in A. Then if A is a Backström order, so is the cross product of A and G. And the same for nodal. If A is a nodal order, so is the cross product. There is another interesting class of orders closely related to Backström orders. I recall that a Coriston order is such that its objective dimension is 1, of itself is 1. It means that A is injective in the category of A lattices, of A models which are free as R models, finitely generated free R models. Consider the endomorphism radical of this Coriston order. It is known, that was proved by Kirichenko and me, that every lattice over A uniquely decomposed into direct sum, P plus M dash, where P is projective, M dash is an A dash lattice. Moreover, and one can easily restore the Auslander right quiver of the category of A lattices if we know that of A dash lattices. That is written in my paper in Ukrainian Mathematical Journal. This is rather easy procedure. Because we only have to find where the projective models must be placed. It is not very good. Okay. And we call it Gorenstein order A almost Backström if A dash is a Backström order. I recall that the Auslander right quiver of Backström order can be easily constructed from the Auslander right quiver of the corresponding quiver. Yeah. So we can also easily construct the Auslander right quiver of an almost Backström Gorenstein. The preceding considerations imply the following: if a group is broken acting on A, then it acts on A dash and so on. And we have the following corollary that if a group G of order n acts of an order A and n is invertible, and if A is almost Backström, then so is the cross product. Now, maybe examples. Let's first of all consider the commutative case. If A is a local ring of a singular point of an algebraic curve. Then it is almost Backström if and only if it is formally equivalent to the local ring of the common point of n plus 1 lines in an in n dimensional affine space, which have a common point, one common point, and are in general position, which means that neither n of them belong to an n-1 dimensional subspace. Now, if we could do 3 lines on a plane like this, or singularity of type D4, as they say in the theory of singularities, it is an example of almost Backström order. If A is almost Backström, then A dash is formally equivalent to the local ring of the intersection of coordinate lines in an plus 1. We just, one of these lines, we move to the space of bigger dimension transversally to that. Okay. One more interesting example, I guess. It is known and not very difficult to see that if K is the Kleinian for group, then it's a group ring over two-adic integers is an almost Backström order. It is, as they say, singularity of type D4 tilde. Therefore, if we have if a group G contains K and such that the index is odd, the group ring ZG is also an almost Backström order because it is a cross product of K and the quotient. And the order of the quotient is invertible in Z2. So it can be used to describe the Auslander-Riemann quiver of the category of G lattices, or of as they say, of integral to adic representation of the group G. For instance, it is so if G is the alternative group of degree 4. Yeah. It gives us a possibility to restore the Auslander-Riemann quiver of integral to adic representation of the group. So they calculate cohomologies and so on and so on. Yeah, I recall that for Kleinian, for group cohomologies were calculated by Andriana Plakosh and me. And yeah, okay. I think that I shall stop right now. And so thank you very much for your patience.